So I want to continue to discuss alternans from the perspective of dynamical system theory, and I will touch on two topics. So the first topic is to predict alternans by estimating the eigenvalue of a cardiac system. It can be a cell or tissue, and using data-driven method. So we're not going to assume a restitution curve or another underlying model. We're going to look at the data, look at the transient response of the data, and by examining how the trajectory change evaluates the eigenvalue so that we can predict bifurcation. Then the second topic is to discuss the difference between two possible pure doubling mechanism, the smooth mechanism, which we're more familiar with, and the other border clearing mechanism, and how to distinguish between the two mechanisms. So I'll start with bifurcation estimation. So starting from the famous restitution model by Nolesko and Dayline, we say that we can describe the relationship between APD and the previous DI, so you get some kind of mapping model. The mapping model tells you that when the slope is greater than 1, we're going to have alternance. So another question is, what if we have a more complex system? What if it's the system is not a simple mapping model? If, for example, Schiffer-Fox model has 16 variables, right? How can we do that? Our Billerud model has how many? 6, 8 variables. So I think Niels has a couple of nice papers to discuss. If you have a ODE model, how do you calculate the eigenvalue using variational method of Floquet theory and so on. So the more practical question is that suppose we collect data from experiments. We don't know how many variables, right? What's the number of state variables? What's the proper state variables? What's the dimension? We don't know that. Suppose you know the state variables. Suppose you know it should be. Suppose we know Schiffer model is a good model. We know we need to have 16 state variables. But the problem is that we cannot measure 16 variables. We can only measure one variable, right? Sometimes at the most 2 variables. You can measure voltage and calcium. And also in experiments there exist noise and so on. So is it possible to estimate the eigenvalue using just the time series of this single verb? That is what we want to do. So I have a few slides here, go through the theory, but I'm going to skip those. So if you're interested, I'll show you this, explain how that is done. But the key hypothesis here is that the dynamical system may have high dimension, right? But we know the essential dynamics probably will locate on a low-dimensional manifold. In other words, the system may have many eigenvalues, but some eigenvalues are small, right? So those small eigenvalues will decay much faster. So the larger eigenvalues will take a longer time to die out to eventually come to this periodic orbit. But the smaller one will quickly die out. So therefore, okay, what do I mean by that? Okay, what do I mean by? Okay, so let us say, think of this problem. Start from eigenmodes, right? Eigenmodes, exactly. So suppose we start from periodic. Suppose that we already are at periodic, right? Periodic response, steady state. So now I give a perturbation. So this will either perturb the basic cycle length or whatever I perturb. So I will be driven away from this periodic. And then if you continue to pace it, eventually it's going to approach your original steady state. Right? And during this transit process, some eigenmode will slowly die out. Some eigenmode will very rapidly die out. Or you can think of, we have, I don't know how to draw this. So if I have a ball, right, this 1D is going to eventually die out. But imagine this is a saddle shape, not saddle, ball, right? But it's steep this direction, shallow that direction. Then it will be much faster, right? If you start an arbitrary kind of oscillation, it's going to mainly focus on that direction. So our hope, our hypothesis is that the eigenmode corresponding to alternance is slow. This is because when it's close to alternance, it's about to approach -1, right? About to approach -1. Because -1 is characteristic for pure doubling bifurcation. And other eigenvalues will be close to 0. Then you have this dominant eigenvalue. Okay, that is the fundamental hypothesis. And then, so hopefully we can estimate those dominant eigenvalues. Okay, so those are the key hypotheses. So now the methodology is this. Our measurement is a one-dimensional measurement, but the dynamic system is a high-dimensional system. How do I estimate this high-dimensional space using a one-dimensional measurement? We can do using the so-called delay embedding technique. By introducing delay, you construct some pseudo-state vector that is high dimension. And then your pseudo-state space will be a map, some kind of transform of the original state space. So that is the fundamental theory of nonlinear dynamics state space reconstruction. So using that. And once you have this pseudo state space, then the question is, I don't know the dimension, right? What is the proper dimension of a pseudo state space? Because if I don't know the system, I don't know the dimension. Then you can do some estimation on the dimension of dominant eigenvalue using principal components analysis, just as one example, or you can use some other statistical techniques. And eventually, you need to compute the dominant eigenvalue, but this involves some optimization statistics, for example, maximum likelihood estimation, and so on, to estimate the number of dominant eigenvalues and the eigenvalues. Oh, they have not only one. Hypothesis is a few, right? Not too many, so that I can estimate, right? So you can think of a cardiac experiment. If I have hundreds, thousands, then we're doomed. But if they're only a few, then I'm going to show you that we can estimate a few.
If I have a dynamical system close to a bifurcation, it will be one bifurcating
right.
mode, and then the eigenvector can have,
right. You have one bifurcating, right? That one's the magnitude is close to 1, right? Yeah, but there are other eigenvalues which probably can also have be less than 1 but close to 1. For example, memory. Accommodation can be close to 1. There can be some other things, not very close to 1, but still significant compared to others, right? Right. Right. Yeah. Yes. So it depends on the system. Okay.
What's
delayed coordinates, for example, using the stock value, for example. So I look at today's stock index and the day before yesterday, then that's a 3-dimensional pseudo vector, okay, instead of 1D. Okay. All right. I'll skip this. Okay. Let me use a numerical example to demonstrate. So I'm using the Schiffer-Fox model. because this is a pretty good model that has a very good voltage from the Fox model and has a well-established calcium cycling from Schiffer's work. So if you simulate this model, you're going to get a bifurcation to alternance. BCL is a pacing period, basic cycle length. Okay. So if we give periodic stimulation, we're going to have 1-to-1, then it becomes alternance. So what we want to do is to estimate the eigenvalue before bifurcation occurs, right? After bifurcation, eigenvalue is already less than -1. So we're going to estimate the eigenvalue for BCL in this region. Okay. So you give a BCL, I'm going to simulate the model, or in experiment, I can stimulate the tissue for some time and then collect the action potential, then using our technique. So we explored several different pacing protocols. Constant pacing, that is the most commonly used technique, right? So you stimulate with periodic stimulation. And you can also do random pacing. So random pacing is probably more similar to the natural pacemaker, right, in the heart. Or you can do alternate pacing, means that I give a longer BCL, then followed by a short one, then another longer one, followed by another short one, and so on. So we studied those 3 different pacing protocols. Okay. Sorry? Okay. In this numerical example, it's a single cell, right? It's the Schiffer-Fox model. That's a 16 ordinary differential equation describes the single cell behavior. Okay.
It's only the ionic model.
Yes. Yes. Okay. So use the constant pacing. We collect the action potential time series data and estimating eigenvalues. You can see this. There is one eigenvalue that is approaching -1. The actual eigenvalue was a circle. The estimation is the star. It's a very good estimation. And the system has another eigenvalue which is close to +1. That is the accommodation. That is the memory. But constant pacing is not able to estimate this very well. It's probably, I don't know, maybe the transient was difficult to capture.
Explain actually how you're estimating this, because if you just use constant pacing and you are
Okay.
one regime,
Right.
basically just going to see that all your state vectors are identical.
Right. So we need to look at the transient.
Right. So basically you start with different initial conditions.
So for example, I will first simulate this at 400 milliseconds to reach steady state. Then I give a change to 375, and I start to simulate at that BCL. And then I'm using the transient immediately after that change. So that shows you how fast or how slow you're approaching steady state. Steady state gives me nothing, right? All the eigenvalues die out, all eigenmodes die out. But the transient in the process to approach to steady state, that is very important information. Okay. All right. So we got a very good estimation for the negative eigenvalue, but memory factor was not able to not able to capture that. But random pacing give better results. So the negative eigenvalue is very accurate. You can see actually it's very close to alternance, and even the positive one was actually estimated. And moreover, our statistic shows that there's 3 dominant eigenvalues, and the third one is very small, right? But that is actually bigger than others because we have the closed form, explicit form of Schiffer-Fox model. You can calculate the eigenvalue analytically, numerically analytical. calculate that, and we show that all other eigenvalues are much small, and this one, the third one, is about 0.1 or something, and that is also captured by this technique. All right, and finally, we do an alternate pacing. But alternate pacing gives us the results, all over the place for the, especially the other two eigenvalues. But the minus eigenvalue is still okay, right? But the problem is that if my concern is about the alternates, then I could do any of the algorithm. But I think the random pacing will be most robust. Right? That's the most robust, probably most realistic. Right? So we hope to be able to apply this technique to real experiments, or maybe to human ECG, right? So consider ECG is some kind of random pacing, because the pacemaker cell have random has variation from bit to bit. Okay. All right. So the take-home message is that we have developed an empirical stability analysis technique, based on stability analysis and statistical estimation. And this technique, because we do not assume any underlying model, not the analytical daily model, not any of the memory model, and so on. So this, therefore, it has a general application, and this can be basically because it doesn't have to be cardiac, right? Like it's any dynamical system. If you have a time series and study the transient response, transient behavior in approaching steady state, we can use that to estimate the eigenvalue. Okay. Questions before I move on?
So how long do you see the signal?
How many bits do I need to have? That is a very good question. Let me see. Probably we use about 10 bits. I don't exactly remember.
It will depend on how
Right. We use about 10 bits, but Nina experiment had only 4 bits, right? But we were able to get some results. So from experiments, although I think she will talk about that.
So then from 4 bits, how do you still use the error in the measurement from the experiment versus the error?
Right, that is a very good question. So the problem is that there are multiple sources of error, right? One source of error will be noise. And also the error in the truncation, right? Because the system has a high dimension, we really truncate it to low dimension. There are multiple so therefore, I'm pushing her to do more bits. So because you have more data, and then that gives you more statistical weights, right? So hopefully, and so of course it's not guaranteed that you always are lucky enough to estimate the eigenvalue. If your noise is too large, your signal is small, it will be buried on the noise. But in well-controlled.
Also, you're probably not completely accurately describing how many bits you need, right? Because your analysis is based on principal component analysis.
Right.
Which requires statistical operation. And that
Yes.
requires certain more than 4 bits in order to extract the PCA amount.
Many random realization.
Right. Yes.
Like 1,000.
Right. No. You don't need the 1,000.
Oh, okay, 300. Right?
No.
Right?
Sure, you could.
Large numbers, you don't have statistics.
Right, you could use that, but in our we didn't use that many. I said 10 bits based on the it's an empirical study, right? The theory is theory, but results is based on empirical numerical simulations.
No, but I mean, if you use a very small number of bits, then you're guaranteed to get poor results for that result.
Of course. So that's why we need more data, right? And the good thing is this: on the natural heartbeats, right? So we know the heartbeat variability. So human heartbeat is never periodic, right? It always changes. And actually, someone maybe Jianbo can claim that it's chaotic, and some people say, okay, it's chaotic. It always has this variation, right? So that means you never come to this fixed point or this periodic, steady state. You always be wandering in the neighborhood, right? And then, so this gives us the advantage that because we can look at okay, if I'm here, I'm close to this, so I'm not going to come exactly to the but I'm going to pass by, right? And then next time I will come by again from another direction. So your overall response will be a combination of those few dominant eigenmodes. And that information is embedded in the transient. That is what we're trying to do. Okay. Questions? Assuming one kind of them. What do you mean? Oh, this is pre-bifurcation. This has to be before bifurcation occurs. So, because after bifurcation, the idea is to predict alternance, not to detect alternance, right? Because detection is relatively easier than prediction, right? If alternance occurs, all I need to look is the variation in this the APD or the magnitude, right? But before alternance occur, your steady state response is period 1, is 1-to-1, right? Your transient may, look, depends on the pacing, right? So you want to tell that how close I am to alternance. Here, this is numerical simulation, but I think Lina is going to show some experimental data. Oh, how do I know it's before bifurcation? So in experiments, what you can do is that you can do this at multiple BCL and you go beyond, right? And then afterwards, you start to analyze data. You say, okay, here is alternance, and here I'm estimating, right? You can go beyond, right? You have to go beyond to know, okay, here is alternance. Right?
So what eigenvalue tells you that you how eigenvalue tells you?
Right. Okay, I see. Right. I'm sorry about that. I didn't emphasize on. So based on dynamical system theory, the idea is that if we have one eigenvalue approach to -1, then that's an indication of a pure doubling bifurcation. So alternance is a pure doubling bifurcation. Okay, so therefore we are looking for a negative eigenvalue, and we want to looking for a trend which is becoming, more and more negative, close to -1.
Technically, it's only true for single cell.
No.
So in
No.
tissue, it's not -1.
Why not?
Pretty much never -1.
Or why not?
Well, because if you have a spiral,
Oh,
the frequency of the
spiral wave is not alternate, right? So we're talking about alternance. Well, sure, you could. Then the question, I don't. That probably is you probably have an imaginary, right, complex conjugate. So, right. So even for fibers, like Alain's model shows that sometimes you have -1. Traveling wave is possible. Traveling wave is a complex conjugate. So that we haven't looked at, but right, complex value is possible. Actually, we're able to estimate a complex if we know this complex. So we haven't tried traveling wave, but definitely, it doesn't matter, right? Because dimension, what's the difference between single cell and fiber? The difference is dimension. From dynamic system, if I have 100 cells, it's just 100-fold increase in the dimension, right? I have some coupling term, just another system, right? So, but I agree it's much more challenging, but.
You are considering that the model is linear.
Okay. Right, this, of course, is based on linear stability analysis, right? Based on linear stability analysis, therefore, the idea is that it's a non-linear system, but we are studying the transient response in the neighborhood of steady state. Therefore, we assume we can truncate high-order terms, right? So linear stability theory. It's based on linear theory. So because based on nonlinear, we don't know the nonlinear terms, right?
So all three models that you suggested can predict
Yeah.
bifurcation because
Right.
all of them could predict the minus
Right.
negative value.
Yes. Yes. Right. So yeah, we use the Schiffer-Fox model because that is a relatively complex model, right? So you can use it in. Huh?
What does this model look like?
What does it look like? I'll let-
Give me other models.
So it's a set of the Hodgkin-Huxley equations, right? So it's
So it's only an ionic model, you say, right?
Ionic
so
model.
it has calcium also. So it has calcium cycling, that equation for calcium transferring between different compartments, kind of a chemical engineering that
How many gates?
Oh, so they have all the currents. Yeah, there'll be, half a dozen gate particles.
Close to rules.
Yes, it's very similar. It has a little more sophisticated calcium cycling, but it's just all these.
More complex than Low-Rudy, right? Right.
Well, if there are 16 variables, therefore some of them are pure, then maybe calcium, maybe two or something, and then the rest is voltage, and then the rest may be so maybe so on the order of 10 gates.
And eigenvalues, we're talking about the eigenvalues of the Jacobian the system.
Yes. Yes. Exactly. Okay. So let me move on to the next topic. So, alternance basically is a pure doubling bifurcation. So if we collect APD at the steady state APD at the different BCL levels, you're going to see a bifurcation curve like this. Well, pure doubling bifurcation occurs in many different systems, right? Almost nonlinear dynamic system, it's possible to, maybe possible to have a pure doubling bifurcation. I'm just giving you a few examples. These are systems I have studied: the electrical circuit, cardiac dynamics, atomic force microscopy, the macro electromechanical system, and all of those systems I studied, they all have they all have pure doubling bifurcation. So bifurcation is therefore a ubiquitous phenomenon. So, according to the classical bifurcation theory, that in order to describe the dynamics of bifurcation, you need to have a smooth function. I mean, continuously differentiable. And another idea is that we can do perturbation analysis in the local neighborhood of this limited cycle or fixed point, depending on how you visualize the system, and you could neglect high order terms. How many terms you can keep lower order terms, linear, second, cubic, and actually a lens model, I guess, based on similar concepts, similar ideas. So this is a relatively well documented field. Starting from the early 90s, and people start to look at another possible, should I call it mechanism, or a set of mathematical formulas. To say, okay, a dynamic system is not smooth. My vector field is not smooth. So there exists some physical boundary. So on one side of the boundary, dynamics governed by some kind of function, another it's another vector field. So because there exists a boundary, on the boundary the vector field may be discontinuous, or sometimes the vector field is continuous, but the derivatives are discontinuous. This is the so-called non-smooth, and especially about the collision. So for example, friction and impact, right? Friction is non-smooth because suppose I'm pushing this cup, so there is a minimum number of using Coulomb friction model, for example. if my applied force is small, this is not moving. The friction force is just equal to whatever force you apply. And then once this start to slide, the friction force is just equal to mu times the support force, right? So you have this discontinuous. And impact is not a problem. Suppose we have a tennis ball, a ping pong ball, you bounce that on the floor, the instantaneous change in the velocity. So those are examples of a non-smooth vector field. Non-smooth vector field may lead to bifurcation as well. So now the question is, pure dominant bifurcation in theory can occur through either smooth bifurcation mechanism or border clearing, and how do we know what is the more appropriate mechanism to describe alternance? So is it possible to distinguish between smooth and non-smooth? That is the question we are trying to answer. So now, let me see. Sorry, I skipped. Did I skip a slide? Okay, so I'm sorry, here. And also, in the literature, there exist many models which using a smooth mechanism, and also there's some, much fewer, but there are few models that border collision type, non-smooth type. And also many of the ionic model, like Flavio showed, many of the ionic model have discontinuous functions. Right? The gate variable have a discontinuous function. Below this voltage, they use one kind of function. Above, they use another. So those are the sorts of non-smooth functions. So we want to distinguish between the two mechanisms. Now suppose I have a very detailed representation of the bifurcation diagram, and then a non-smooth curve we open with a certain angle. The smooth curve is smooth, and here at the bifurcation point, the two branches become tangent. So that is very easy to tell, right? If you look at the bifurcation diagram, I can say, okay, border collision, non-smooth or smooth. But in experiments, you don't have that many data points. You have just a few data points, and it's difficult to tell, separate them. So we have developed the technique. What we use alternate pacing. I already introduced what this is. So you alternate the pacing interval, and so therefore we can think of the pacing as a baseline value in the middle average value, perturbed by a long short pattern. Okay, so a perturbation of it. So therefore, the pacing protocol has two parameters, right? The baseline determining how far you are away from the bifurcation, and delta, this perturbation depends on how much the amplitude of your perturbation. So then using this alternate pacing protocol, we can simulate or stimulate cardiac tissue. So now the blue dots show the response on the regular constant pacing experiment. You see a bifurcation to alternance. So then the red dots shows alternate pacing now at this 850. So the constant pacing response was, I don't know which point I'm pointing to. It's 1-to-1, but because my pacing now has perturbation, so my response will have large, small, right? So then calculating the difference between those large, small APD, divided that by the size of the perturbation. So that gives you some kind of measurement on the amplification effect. I can think of this as an input-output system, right? I think of the pacing as input. So my input has noise or perturbation, and then my output has the response in APD. So I want to see, okay, how this is amplified. So the idea is that the system become more and more sensitive when you approach to bifurcation. Near bifurcation, the system is very sensitive, so that certain perturbation will be amplified. And then according to the response, we can tell what type of bifurcation it is. That is the idea. So since there are two parameters to play with, one is the perturbation size, another the baseline BCL, and we calculate some kind of amplification gain. And for the smooth bifurcation, you get a smooth curve, and the decaying non-smooth bifurcation, you got also a decreasing curve, but it has some non-smoothness. But again, using discrete data points, it's difficult to distinguish between them. However, if we now fix the baseline, BCL, and then we change the perturbation size, and we're going to see a qualitative difference in smooth versus non-smooth bifurcation. And therefore, this qualitative trend change will be a useful tool for you to distinguish the two types of bifurcation. So we have done some numerical simulations, show you the analytical results are in the solid curves. Theoretical predictions are using dots to validate our theory for both smooth and non-smooth. So some experimental motivation to study non-smooth bifurcation, I think this was probably the same set of data Flavio included in his talk. That's from Gilbert et al. In 1984, and also look at the more recent data from Diaz et al. So that one-to-one response is almost represented by open circles. They almost lie on this straight line. And the alternate response, when it's in alternate, then actually, so some points are on the original curve, some points on another steep curve, another curve with a steep slope. And what? This is the calcium. So this is the calcium amplitude, and some calcium atom. I don't know that. So they measure the intracellular calcium concentration, maybe within SR. Okay, within SR, measure the amplitude. Peak calcium. Okay, thank you. Peak calcium.
Calcium has an amplitude, so the peak of the calcium concentration in the cell.
Can we measure to nanomolar? Actual experimental measure to nanomolar scale? Really? That would be quite amazing.
Equal accuracy of tens of nanomolar.
Oh, maybe this can be. This probably is calculated, right?
It's with dyes.
It's probably it's with dyes and probably the scale.
Hmm? Diastolic interval. Okay, so if I fit the restitution curve from restitution data from Gilbert et al., I can do that using smooth and non-smooth curves, and they both fit the restitution curve well. But if I use the model to predict alternance, like the model with non-smooth feature will predict that much better. So this is a very interesting. This calcium data is a very interesting set of results. I think Schiffer incorporate a similar relationship in his calcium model, and so actually we have recently shown that let's neglect APD, just look at the calcium, assuming the voltage clamped experiments, and then if you adopt this kind of calcium relationship, then you can lead to very interesting dynamics. The idea is that so you can have a period 1 response that become alternates, or by changing the relative slopes between the two curves, then you can get a immediate transition from period 1 to period 3, period 1 to period 4, 5, 6, even to chaos, and so on. So this is so-called instant chaos. So the classical work of the Maryland chaos group show that period 3 indicate chaos. The idea is that in smooth system, you have to have chaos through a period doubling cascade. Okay, period 2, period 4, period 8, eventually to chaos. Once you have chaos, then you can have anything else that immediately come out of chaos. So it's not possible to go from period 1 to chaos. But the non-smooth system is possible to jump from period 1 to chaos. Of course, these are just theoretical exploration, right? Just say, okay, suppose we have a calcium function in this form, then it's possible to have such. But probably experiments need to be done to validate.
Could you say again what's the difference between the different panels?
Okay, so by choosing different slopes, I can get this, that, or different ones.
You do it with iterative map or
Iterative map.
iterative map would give you VO2?
Yes, yes. It's a very simple map. It's just
So what is the restriction that there's no minimum restorative interval for calcium? Or you see
there is. You could have that. So all I did was to change the magnitude of slope 1 and slope 2. By using different combinations, it's possible to have those. So, of course, I was playing this on my computer, and I may have chosen some unrealistic number, right? But we don't know the experiments. Maybe so then more experiments probably need to be done to say, okay, what are the possible range of the slopes, and then we can focus more on that range. Okay.
This is a
Monotonic
monotonic map.
map, yes, 1-to-1. But it's not smooth. It's basically 2 straight lines. I just use this map. So this is linear. This is a straight line. That is a straight line. But
I can see the bifurcation coming from the field here, I see how you get it.
You can get anything that you want, right?
No, but just by making it
It's really just a matter of, it's down to right
but you just
condition.
smoothed it out really smooth.
no.
That based on the slopes, you can get periods of any multiplicity.
Yes.
Once you cross the
Right. It's not the issue of amplification or fine details. It's not, but the real physiological phenomena. What is that? We don't know. Just that in this theoretical model, you just immediately go from 1 to 3. That is what is happening. Okay, so I just want to say that bifurcation is a ubiquitous phenomena, and we have proposed this alternate pacing technique to distinguish between the 2 responses, and there's a few papers can show the details of our work. Before I stop, I want to tell you a little bit about the other relevant work my group has been doing. So we have been developing computer models to simulate the cardiovascular dynamics. So particularly, we are looking at the interaction between mechanical function and electrophysiology phenomena. So we have developed a finite element-based model that can run on supercomputer, but Flavio's GPU is much cool, so probably wait to that too. So, okay, so I have also been doing some signal processing of ECG. So what we did was to using signal processing techniques, nonlinear dynamics, and machine learning techniques to study ECGs. We have done several work to fill in if the ECG record there was a gap, means that you missing the signal for a limited amount of time, and we have a technique to fill in the gap, and also we have a way to estimate the error, the noise level, the quality of the ECG, and to detect the human errors. For example, a nurse takes ECG, she may make a mistake by switching two electrodes. So we can detect that to a certain degree. So I work on a couple of awards in the FieldNet Challenge in the past years. Okay, so currently we're developing a cloud-based ECG analysis software. So we want to, goal is that this will be a tool for user to upload the ECG and then to do some preliminary analysis, maybe give indication of risk for certain cardiac diseases. That's what we're currently doing. Okay, so I want to thank my students, former students, and current students, and collaborators for their work. And I'll be happy to take any other questions.